You know about this. And please remember the altered version of question 3 from bonus quiz 1, which I offered you. That your solution to that is also due on Tuesday of week coming. Now, although many of you have seen this, again, since different discussion class gatherings made different degrees of progress, since I want everybody to have the same foundation, recall that, which we talked about in brief at the end of last gathering. The solubility of calcium carbonate in a water solution buffered at pH 8.00 is, number one, recognized to be greater than the solubility of calcium carbonate in straight water. Why do we know that? Because in straight water we get a saturated solution pH of 10.0. Here we have a water system buffered at 8.00. This is 100 times more acidic. That doesn't mean this system is acidic. We're making a comparison. It's 100 times more acidic, or if you prefer, 100 times less basic than pH 10.00 or pH 10.0. That guarantees, since this system is more acidic, carbonate ion is destroyed more effectively. And the more effectively you destroy carbonate ion, the greater is the solubility of calcium carbonate. Because to make calcium carbonate, you've got to have calcium ion interacting with carbonate ion. So if you do anything to reduce the solubility, the stability of carbonate ion, you certainly have to increase the solubility of calcium carbonate. The equilibrium to be considered is this. Did you recognize when you looked at this equilibrium that it's a non-stoichiometric statement? You remember what non-stoichiometric means for a reaction equation? If you read this reaction equation, if it were stoichiometric, it would say, by this reaction, per mole of calcium ion produced, you'd also make an equivalent quantity of bicarb ion and hydroxide ion. But that's not true. Because the hidden part of the chemistry of this system is not revealed by this reaction equation. What is this hidden part? There is carbonate ion still in the system. If you recall, regarding calcium carbonate dissolving in water, we found that carbonate ion was converted to an extent on the order of 70% at pH 10.0 to bicarb and hydroxide ion. Well, then 30% of the carbonate ion is still there. That's why this reaction statement is not stoichiometric, at least not at pH 10.0. Is it possible that this reaction statement might be stoichiometric at pH 8.0? No, still can't be stoichiometric. At least not for all products. Because we fixed the hydroxide ion concentration by buffering the system. But is it possible that at pH 8.0, the molarity of this and the molarity of this are equal? Well, what do we do to find out? We know that the various forms of carbonate-containing things, material balance for carbonate, are carbonate ion itself, bicarb ion, when carbonate ion gains 1 H+, and hydrated CO2, quote-unquote H2CO3, which is what you wind up with after carbonate ion gains 2 H pluses, or after bicarb ion gains 1 H plus. So what we have to do to see if this reaction equation is stoichiometric with respect to these two products is to see if in this system the only carbonate containing species of consequence is bicarb ion itself. Well, how do we do that? You did that. At least most of you did this. And it's in the notes. You write reaction equations, which is a function of pH. Relate the possible forms of carbonate ion to each other. What am I talking about? Well, if we focus on bicarb ion, we recognize that if bicarb ion reacts with water as an acid, you make hydronium ion and carbonate ion as products. So there's a reaction equation which relates the two carbonate-containing species, bicarb ion and carbonate ion itself, as a function of pH, because that reaction equation contains hydronium ion. Now, if we want to get a handle on hydrated CO2, quote-unquote H2CO3, then we write Kb for bicarb. Because when bicarb behaves as a base and reacts with water, we make hydrated CO2, quote-unquote H2CO3, and hydroxide ion. So we got the reaction equations we need to get at material balance for all possible forms of carbonate ion. And when you take these two reaction equations, which again most of you have done, and rearrange so as to get a ratio of the molarities of bicarb to carbonate ion as a function of hydronium ion concentration, which means you're using the Ka bicarb equilibrium reaction, or to get a ratio of bicarb ion to the molarity of hydrated CO2, which means you're using Kb bicarb, you find that at a pH of 8.00, where the hydronium ion concentration is this, where the hydroxide ion concentration is this, the molarity ratio of bicarb to carbonate is 210 to 1, and the molarity ratio of bicarb to H2CO3 is 42 to 1. Does this sound like we've established that bicarb ion at pH 8 is certainly the principal form of carbonate ion? Sure. Well then, if the other forms of carbonate ion beside bicarb need not be considered, because we've demonstrated that bicarb is by far the principal species, then all the carbonate which goes into solution by this reaction becomes bicarb ion. There's no residual carbonate ion to speak of, 210 to 1, and there's certainly no conversion to H2CO3 of an extensive nature, 42 to 1. So we've established that that relationship is stoichiometric between calcium ion and bicarb ion. Consequently, since we've also realized that when calcium ion goes into solution, it doesn't do any other chemistry. The solubility of calcium carbonate in any water solution system of calcium carbonate is equal to the calcium ion molarity. Because the formula for this material, calcium carbonate, says if I dissolve a mole of this, I'm putting a mole of calcium ion in solution, and at the same time a mole of carbonate ion in solution. We've already realized the mole of carbonate ion doesn't sit there. Participates in acid-base chemistry. Not calcium ion, it doesn't do anything. It forms a defined hydrate, but Ka for this defined hydrate is on the order of 10 to minus 14. That's such a feeble acid, that's not going to do anything to pH. practically speaking. Certainly not if it's present in solution at a very small molarity, and we know the solubility of calcium carbonate in water isn't very great, so we're never going to get calcium ion in there at a particularly substantial molarity. What are we talking about? The chemistry of the system. That's the hard part, but that's the part that underlies understanding what the heck's going on here. So, we go back to our K expression for that reaction, which you recognize is evaluated as 1.3 times 10 to minus 12 because this K is really equal to, as I wrote up there, the solubility of calcium carbonate multiplied times Kb carbonate ion. And after having established that, the molarities of calcium ion and bicarbonate are equal, and the molarity of calcium ion we already know to equal the solubility of calcium carbonate. We can say S represents this molarity, which we know, and S also represents this molarity, which follows from this analysis. The hydroxide ion is fixed. That's 1.0 times 10 to minus 6. Do the arithmetic, there's the solubility. How does the solubility at pH 8 compare to the water solubility when we're using straight water as the solvent and a solution pH of 10? There's that value. Well, if you do the arithmetic, you see this is about 8 times bigger than this. So we know the arithmetic we've done is certainly in keeping with the chemistry of the system, because before we did any calculation, we convinced ourselves that whatever the solubility of calcium carbonate is in this system buffered at pH 8, it's got to be bigger than this number. Now then, before we proceed with analyses like this, let's go to the salt effect, which is also part and parcel of considerations which apply to equilibrium systems that involve salts of limited solubility in water. The difference in the main, however, between the salt effect and the other considerations which we have made is that the salt effect is not a chemical effect. It's an electrical effect. It's an effect based on Coulomb's law. An effect which depends on the fact that oppositely charged particles attract each other strongly. Example. At the start of chapter 19, you looked at the solubility of silver chloride and the equilibrium established when silver chloride is dissolved in water. We commented that you really do get other species other than silver ion and chloride ion when you saturate water with silver chloride, but in the main you get silver ion and chloride ion. So we will conclude that the solubility of silver chloride is adequately represented by the square root of the solubility product constant for silver chloride, because we know from an acid-base standpoint this thing has no effect on pH. It's a conjugate base of hydrochloric acid, a strong acid. Upshot, this is a weaker base than water. Does it exert any effect on pH in water solution? How about this? If you were in laboratory and I charged you with the responsibility, you're in 46 laboratory, I give you the responsibility of proving that silver ion's presence in water solution has no effect of consequence on pH. What would you do? What would you do to verify this? You're in the lab. I want you to do one or more experiments as necessary to verify this statement. The presence of silver ion in water solution doesn't exert any effective consequence on pH. Now I'll tell you that silver ion does also form a defined hydrate. Here it is. It's a dihydrate. Just for fun, what do you think the shape is of this thing? It's got a silver ion in the middle and two water molecules stuck to it. So it's rather like a three-particle system with the silver ion in the middle. So there are only two possible shapes. Well, actually, there's three possible shapes. Silver ion, one water molecule here, and the other water molecule someplace else with respect to the water molecule that's here. You think the other water molecule will be right here? How about here? How about here?
No.
How about here? How about down here? Well, if I tell you that there are no non-bonding electron pairs on silver ion that exert an effect on geometry, what conclusion would you reach? Linear? sp hybridization for silver ion? You remember the sp hybridization corresponds to a 180-degree bond angle in linear geometry? And you're right. That's what it is. If it wasn't linear, it'd have to be bent or angular. And the remaining possibility is, if you envision the possibility of a bond between the water molecules, a triangle. But no, it's not a triangle. It's linear.
So what happened to the electrons that surround the silver atom?
We'll talk more about that in chapter 23.
Okay.
Where we will spend time in an extensive fashion. Oh, pardon me, chapter 24. When we talk about coordination complexes of transition metals. A silver ion is derived from silver, which is a transition metal. We'll get at that in extensive fashion near the tail end of this gathering. So, I repeat my question. What are you going to do if I tell you that silver does form this defined hydrate, a dihydrate, and therefore certainly can behave as a Bronsted acid, because hydrated metal ions, as we've already recognized, often have the capacity to behave as Bronsted acids. But I make the statement to you that hydrated silver ion in water solution does not exert any effective consequence on pH. What experiment or experiments will you do to prove this? You're in lab. What are you going to do?
Add like a soluble silver salt, like silver nitrate, and then...
Well, in laboratory. Do you have silver nitrate solution on the side shelf?
I don't think so. Alright, maybe...
Are you in laboratory?
Yeah.
Did you recognize that the only silver ion containing solution you have for your use in laboratory is silver nitrate solution? Because most silver salts are not very soluble at all. Nitrate ion, however, forms all soluble materials. That's why in 2046 laboratory assignment 2, you learn this fancy method to test for nitrate ion. Remember the fancy method? You had to react nitrate ion with iron plus 2, which reduces nitrate ion to NO. And then iron plus 2 also has a habit of forming a coordinate covalent bond interaction with NO. And when this bond interaction takes place, you make a stuff which is brown in color. All that fancy stuff to test for nitrate ion, because you can't precipitate nitrate ion. Nitrate salts are too damn soluble. That's why silver nitrate is the silver-containing material which we use when we want to make a solution in laboratory that's got silver ion in fairly high concentration. Now, silver ion is also expensive. That's why we only use 2/100 molar silver ion solution. The silver nitrate solution you have available for use in lab is 2/100 molar. Well, if you want, I'll give you some additional silver nitrate and let you make 10th molar silver nitrate solution. What are you going to do with this 10th molar silver nitrate solution? Remember the question. You're supposed to verify that silver ion in water solution does not exert any effective consequence on pH. You got 10th molar silver nitrate solution in a beaker or flask. What are you going to do with this solution?
Drop bromothymol blue in it.
You're going to put bromothymol blue in there and look for what?
The color, if it's green, then it's close to neutral, right?
Yeah. You're going to do a pH test. We'll even let you use the pH meters. Remember, you used pH meters for the first experiment in 46L? That'll give you a much more reliable pH result. The indicators only give you a gee-whiz pH result that's good to one significant figure at most. Yeah, that's what you do. Because you know nitrate ion is the conjugate base of strong acid nitric acid, right? So nitrate ion in water solution does not affect pH. So if silver nitrate solution shows a difference in pH relative to deionized water, it has to be because of silver ion in the solution. So if the silver nitrate solution shows the same pH as your deionized water solvent, guess what? That's not doing anything measurably. Which is why, when I write this equilibrium containing silver ion AQ, I don't need to keep the water molecules tacked onto this because its acid strength can be neglected. Same thing for calcium ion. Calcium ion forms a defined hexahydrate. But if you did the same kind of chemistry we just talked about and took a fairly concentrated solution of calcium ion, like calcium nitrate solution or calcium chloride solution, where again the anion doesn't do anything to pH, and observe solution pH, we're the same as deionized water. That's why I don't hang the water molecules on calcium ion when I'm dealing with a reaction occurring in water solution and calcium ions involved. You think I'm going to do that if I got aluminum ion in solution? You think I'm going to do that if I got iron +3 in solution? Hell no! Those hydrated metal ions have a significant effect on pH, particularly the hydrated iron species. All right? Now we get back to the salt effect. There's the solubility of silver chloride. Square root of KSP, because these don't have any acid-base property. So there's another equilibrium you have to pay attention to get solubility. Now then, if we take silver chloride and shake it up in 1.0 molar sodium nitrate solution, recognizing that sodium ion doesn't react with anything in this system, unless you believe these stupid textbooks that write NaClAQ, or whatever the hell that is. Nor does nitrate ion. We just talked about silver nitrate being a soluble material. So if I put silver chloride in an atmosphere that's rich in sodium ions and nitrate ions, knowing that no reaction occurs for the components of this system with sodium ion, nor does any reaction occur with the components of this system with nitrate ion, and then make the observation that the silver chloride solubility is a heck of a lot greater than 1.3 times 10 to minus 5, what's going on here? I think it's considerably greater. So we'll put the double arrow in there. What's going on here is the salt effect. Coulombic interaction between the ions in the sodium nitrate solution, sodium ions and nitrate ions respectively, is what drives this increase in solubility of silver chloride. You think nitrate ions will be naturally attracted to silver ions? You're damn right. Nitrate ions are negative, aren't they? They're naturally attracted to anything that's plus. So here's a bunch of these nitrate ions going to swim towards silver ion. Now they're not going to swim by themselves because the sodium ions are going to swim along. Because the sodium ions are also attracted to nitrate ions, and in this system there's a whole lot more sodium ions and nitrate ions than you have silver ions. But here's this big bunch of nitrate ions and sodium ions going to swim over and wrap around silver ion. They're going to do the same thing with chloride ion, where now Na plus is going to be naturally attracted to chloride ion because the chloride ion is minus. So here's this big bunch of sodium ions and nitrate ions swim around and they wrap around chloride ion. So you got like this cloud now. This is an ion cloud. Doesn't that look like an ion cloud? Besides a bunch of chalk dust? You got an ion cloud of sodium ions and nitrate ions wrapped around silver ion. And an ion cloud of sodium ions and nitrate ions wrapped around chloride ion. What is the effect of these formed ion clouds? Do they stand in the way of silver ion and chloride ion reacting with each other? Yeah. They now shield silver ion and chloride ion from getting together with each other. Because the only way you can make silver chloride is if silver ion and chloride ion conk each other. You now have stood in the way of silver ion and chloride ion conking each other. Result? You can now put a whole lot more silver ion and chloride ion in solution. Because they wind up being prevented from reacting with each other. So if you were, for example, to evaluate the solubility product constant for silver chloride in sodium nitrate solution, here's the solubility product constant for silver chloride in straight water. The solubility product constant for silver chloride in this solution is a hell of a lot bigger than that value. I don't know what it is. I don't know if anybody's estimated it. Since this is not a chemical effect, chemists are not all that concerned with it. But it's nevertheless an effect on solubility. And that's the salt effect. Enough said. Back to chemistry. Here again is a topic which most of you have done. And clearly, this is a topic which you have been pursuing regularly in laboratory. Is it not the case that in 46 laboratory you have discovered that the presence of potassium ion in water solution can be confirmed by precipitation with this rather fancy anion cobalty nitrite? You can do the same thing with ammonium ion. Then when you went to assignment 3, you found out that calcium ion is a good deal more reactive than sodium ion and potassium ion, at least as far as precipitate formation is concerned. Same for ammonium ion. Is that surprising to you? Why is calcium ion expectedly more reactive than sodium ion and potassium ion and ammonium ion? Which you know from a precipitation formation standpoint. Why?
Because it's got a 2 charge?
Yeah! This thing is +2. It's certainly going to, from a charge standpoint, attract negative ions more strongly. Well, the more strongly a positive ion attracts a negative ion, the greater tendency for a reaction. And the lower the solubility of the resulting compound, like calcium carbonate, where you've got an interaction between a +2 ion and a -2 ion. Gives you stuff that's pretty stable, isn't it? You already know this stuff. Teacher's favorite weapon, not very soluble in water. Now when you went to assignment 4, you learned how to test for aluminum ion by precipitation and magnesium ion by precipitation. And when you go to assignment 6, you're going to do precipitate formation investigations on copper ion and zinc ion and silver ion. So far all you've used silver ion for is to find chloride ion. But you're going to do some specific chemistry on silver ion when you get to assignment 6. So you know about this. Now then, if you intend to test for an ion, like specifically calcium ion by precipitation, find out if this ion is in or not in a solution. You take a solution that's rich, that means has a high concentration of an anion, which you know will react with calcium ion and make a precipitate. What are such anions that you learned about in laboratory? Hydroxide ion, carbonate ion, sulfate ion. And another form of carbonate ion, bicarb ion. Each of these ions readily react with calcium ion to make precipitate. The precipitates respectively are calcium sulfate, dihydrate, which geologists and other folks call gypsum. You familiar with this stuff? Do you know that calcium sulfate dihydrate is the principal ingredient in construction wallboard, plasterboard? Some folks call it sheetrock. Any of you people ever hang any sheetrock? Make walls at home? Yeah, I've done it too. Tell me, you want to make walls in home out of sugar? How about salt? Why not? If you live in a perfectly dry atmosphere, it'd be all right.
You don't want horses to eat your house.
What is that?
You don't want horses to eat your house.
You want horses to eat my house? No, I'm not going to make the house out of hay or carrots. But I suppose what you're telling me is that horses like sugar, which I believe they do.
And salt.
Salt. Oh, those doggone horses. All right, I'll keep away from horses. I mean, can you imagine what life would be like when you as a little kid, you go to the wall and you make a smudge. Little kids are good at making smudges on walls. Okay? Mommy comes along, gives you a whap. No more smudges, please. You go away. And then Mommy takes a damp sponge or soapy cloth or something, and she proceeds to remove the smudge that you've created. Well, hell, if that wall is made out of sodium chloride, oh my. Look at this big hole in the wall I now have. You don't do that. Now then, what the notes show you, and it's simple arithmetic. If I have a solution that's rich in sulfate ion at 10th molar, like sodium sulfate solution, another solution that's rich in hydroxide ion, like sodium hydroxide solution 10th molar, another solution that's rich in carbonate ion, like sodium carbonate solution at 10th molar, which precipitate is easier to form? It's calcium carbonate. How are we going to prove this? In other words, I have a solution in the laboratory. I want to know, does it or does it not contain calcium ion? I have a choice of adding sulfate ion 10th molar, or hydroxide ion 10th molar, or carbonate ion 10th molar. I'm going to pick the 10th molar carbonate ion, like 10th molar sodium carbonate solution, and add it to the solution which may or may not contain calcium ion. Because calcium carbonate is easier to form in water than these other precipitates. Which is another way of saying, in straight water, calcium carbonate is less soluble. It's more stable than these other things, and easier, therefore, to form. So testing for calcium ion by carbonate precipitation is a more sensitive, reliable way to get the job done. The proof lies in analyzing the respective equilibria that are established in a saturated solution of each material. Here it is for gypsum. Well, in the 10th molar sulfate ion solution system, the equilibrium molarity of sulfate ion will be 0.10 plus S. S is the solubility of calcium sulfate. S represents the contribution to the sulfate ion molarity made by dissolving calcium sulfate. S, however, will be strictly the calcium ion concentration, because I haven't added any source of calcium ion. So if for this equilibrium I can evaluate S, I will at the same time be calculating the solubility of calcium sulfate in a solution in which the sulfate ion is present at a molarity of 0.10. Well, then I write the KSP equilibrium constant expression. I see that it's equal to this. And as soon as I look at this, I know when I solve this, I don't need that in there. I know that the value for S is so small that when I add it to 0.10, I'm not going to change 0.10. How do I know this? I make a point of this because, again, many of you folks who have difficulty with this stuff have difficulty because your arithmetic skills are not good. And we got to sharpen up those skills. I know you all got the ability to do it. Well, let's take the solubility of calcium sulfate in straight water and recognize that that is fairly estimated by taking the square root of the KSP for calcium sulfate, because we know calcium ion goes into solution, doesn't do anything else. Sulfate ion goes into water solution. Is it fair to say that practically sulfate ion also doesn't do anything else? Do we know that Kb sulfate ion is 8.3 times 10 to the minus 13, which tells us that sulfate ion is an awfully damn weak base. So conversion of sulfate ion by reaction with water to hydrogen sulfate ion and hydroxide ion respectively is negligible, practically speaking. Well then, that tells me that the solubility of calcium sulfate in straight water, which is the square root of this number, is 3.0 times 10 to the minus 3. That's the solubility of calcium sulfate in straight water. Now then, before I do any arithmetic on this, I now am trying to dissolve calcium sulfate in a solution that's rich in sulfate ion. Before I do any arithmetic, I know that the S value for calcium sulfate in this solution, which is rich in sulfate ion, must compare how to 3.0 times 10 to the minus 3, which again is the solubility of calcium sulfate in straight water.
Must be much smaller.
The solubility of calcium sulfate in the sulfate-containing solution has got to be a hell of a lot smaller. Le Chatelier's principle tells me, if you're operating on this equilibrium, and this equilibrium lives in a beaker or flask on the bench top, and you add an external source of calcium ion and or an external source of sulfate ion, what reaction do you force to take place? Left to right or right to left? You force this thing to take place if you add either this or this. That's telling you, solubility of calcium sulfate just went down. And that's easily verified by this arithmetic, which gives us a solubility value of 9.1 times 10 to the minus 5, which is a lot smaller than 3.0 times 10 to the minus 3. Well, I play the same game to get the solubility of calcium hydroxide in 10th molar sodium hydroxide. I get this. You do the arithmetic. The arithmetic is slightly more complicated because in this equilibrium per mole of calcium ion, you got 2 moles of hydroxide ion. And for the 10th molar carbonate solution, you get, based on arithmetic that's immediately analogous to this, you get 6.2 times 10 to the minus 8. Because over here you'd have carbonate ion, you'd have S plus 0.10, and now the KSP value is 6.2 times 10 to the minus 9. So if I know that S is a hell of a lot smaller than 0.10, which it surely is, then the solubility of calcium carbonate in 10th molar sodium carbonate solution is going to be KSP value, which is this, divided by 0.10. And that's 6.2 times 10 to the minus 8. Now I wrote over here is this exact. Let me ask you a question this way. I'm going to the laboratory. I pick up my bottle that's labeled 0.10 molar sodium carbonate. What does that bottle label tell me? The M sub I value. It tells me for every liter of that solution which the stock folks prepared, they dissolved 1/10 of a mole of pure sodium carbonate. Okay? This we know. Question: is it fair to say that in that solution the carbonate molarity is 0.10? I know it's fair to say that in that solution, the sodium ion molarity is 0.20. Is the carbonate ion molarity 0.10?
We're saying no, it should be a little bit less
A little bit less. Why?
because it has basic characters.
Because carbonate ion is a good base. Not a good base, pardon me. A weak base, but a weak base whose ability to change pH is certainly immeasurable. It's certainly measurable. So it's true, it is true that the carbonate molarity in my bottle labeled 0.10 molar sodium carbonate solution. Carbonate molarity might be a little bit smaller than that. How would you find out? How would you find out what the true carbonate molarity is, carbonate ion molarity in 0.10 molar sodium carbonate? You know how to do that now. You take Kb carbonate ion and find out to what extent carbonate ion has hydrolyzed by reaction with water at a molarity, initial molarity of 0.10. That's not hard. Now then, with all of this, we've now laid foundation to go to question 1912 and the remaining body proper of stuff, which is on solubility of semi-soluble salts, which means by chemistry, how do I change the solubility of a salt of limited solubility? And there's all kinds of ways. And really, we've already done some of those ways. Because when we did the solubility of calcium carbonate in a water system buffered at pH 8, that's really a chemical effect. Because at pH 8, you're going to kill carbonate ion more effectively than pH 10. Now we're going to do this in a much more extensive fashion. So here's the question. In a water solution buffered at pH 6, can I more easily form calcium sulfate or calcium carbonate? Imagine you're in the laboratory. You have a soluble unknown. You don't know yet if it's got calcium ion in it. You dissolve some of the soluble unknown in accord with the directives that are in the 46L lab manual. You do a pH check, because that's the first solution test you're supposed to do on any solution of a sample. Because you can learn more from a pH test result than from any other single test. And you find out that the water solution is has a pH of 6.0. The water solution has a pH of 6.0. Okay? This question relates to that, obviously. You now go to the laboratory side shelf. You know that at pH 6.0, you sure as hell aren't going to form calcium hydroxide. You have sodium sulfate solution half molar and sodium carbonate solution half molar. Which solution are you going to use to add to the solution that you're wishing to test for the presence or absence of calcium ion? Which solution are you going to use? That's what we're going to analyze in detail at the start of next gathering.